Okay, so let's get started with the Gaussian splitting. So last time we started to discuss the problem of the novel view synthesis. The basic idea is that if we have some kind of the given a collection of the 2D images that are captured from all different views, we want to basically synthesize a new image from the basically new viewpoint. And for that, the basic idea that was really successful in the null pipeline was basically doing some kind of the reconstruction of the 3D, but not into any kind of solid form, but into any kind of the volume, in a way that we can have some kind of the more the flexibility in the 3D reconstruction. And then for that, like what we need to do is that we are not using the typical some kind of the rendering equation, but we need to actually incorporate some kind of the volume rendering equation. So that's why we start to see this kind of like the volume rendering the equation. Here, basically, there are basically three components. Like one is about the opacity. It's just about like how likely the ray will hit something at that point along the ray. And the radiance is basically some kind of the emitted, some kind of color information emitted into the specific direction at that point. And based on the opacity information, we are also calculating the transparency, which becomes some kind of the non-increasing function. So here, basically, transparency basically meant like how likely the ray will basically travel until that point without hitting any kind of things. So if we multiply both the transparency and the opacity, that becomes the probability, like how the ray will basically travel onto that point without hitting any things, and then stopping there with some kind of collision at the point. And we also derive some kind of the discrete form or like this kind of the integral. This was basically converted like this. So you could see that this really becomes some kind of the calculating the expected value of the emitted light information with the probability term here, which was basically defined as kind of the multiplication of the transparency and the opacity. So this was kind of the basic deformulation. And see, one thing that I really like to basically remark here is that while this was kind of very recent paper, which was like published in 2020, the basic idea that we are basically having some kind of implicit representation for the 3D and doing some kind of the volume rendering was actually quite old idea. So this was actually the case that we are revisiting some kind of some old ideas in the graphics in a way that we are integrating this idea in the neural net so that we can do some kind of 3D reconstruction with some very classic ideas in the computer graphics. So this was really a nice example. And actually you can find that there are some kind of the multiple previous works more than like 20 years ago, or about like 30 years ago for some of the cases that are basically introducing some different ways to define this kind of the implicit representations. So I'd like to recommend you to check out this kind of old work. So sometimes there are some kind of the hidden gem in some kind of the old work that can be really revisited and basically get some like shine again in some kind of the recent neural literature. Actually, yeah, so those are all the cases that we are only using some kind of implicit representation. And after that, like the people also started to look into making some kind of the hybrid representation, basically combining some, implicit representation and the explicit representation. So since this is not the neural network course, so I'm going to skip some details and briefly just go over some basic ideas. So there are some kind of the previous work, which is also utilizing some kind of voxel representation. So instant NGP was also one of the very famous cases that is basically, reducing the computation time of the reconstruction and also the rendering dramatically. So it does really be able to basically reconstruct some kind of 3D scenes in some minutes or even in some seconds, in a few seconds, while basically taking lots of the memory with some kind of 3D buffers. And triplane was kind of the good trade-off in terms of not taking too much of the memory, but still basically, reducing the computation time for both the reconstruction and also the rendering. Not having some kind of every single box on the 3D space, but representing all the kind of quantity at the point in the 3D space as kind of the combination coming from the projected point in the three the planes, like XY plane, YZ plane, and ZX plane. So by having this kind of the three planes, we could basically have some kind of the interesting trade-off, like when combining some implicit representation and also the explicit representation. So point cloud-based rendering was also the interesting case that we are basically having some sort of the rough the reconstruction of the 3D shape into the point cloud and doing some kind of the same the volume rendering by the shooting the ray and basically checking some kind of the nearest kind of the points along the ray. So this is kind of also some sort of the base work that we are also going to discuss in the Gaussian this Splatting. And also there are some kind of previous work which was also using the mesh as kind of the some sort of the rough structure for the 3D shapes and basically adding some kind of the neural the attributes over the 3D the surface of the mesh. And the main thing that we are going to discuss for today is basically the splat-based representation. So here basically the idea is that we are now basically having some sort of the some 3D Gaussians as kind of the some basic primitives. So instead of like using the points, which only has the the position information, now we are defining some kind of 3D Gaussians, which becomes some kind of the point and some kind of small volume in the 3D space, in a way that they can basically have some kind of the better expressions for the 3D shapes. So let's get into some more details about the Gaussian splatting. I guess most of you have seen this video. Let me replay this again. Yeah, so I guess many of you would be familiar with this video. So this was not just like video that was captured in the real scene, but actually it's really kind of the video by just like navigating some kind of the reconstructed virtual 3D scene. So what they have done is that they just like capture some kind of the lots of the images from the some real scene and did some kind of 3D reconstruction using the Gaussian splatting algorithm, and then navigating some kind of the reconstruct scenes by just like changing the position and the viewpoint. So it's like we really navigate some kind of the space in the game, like we are basically doing this kind of some rendering. You could see that these are like all the rendered in real time. So this was the case like having the 16 frames per second in the rendering, and also the reconstruction takes like a much small amount of time compared to the node. So this was basically very interesting work in terms of that it could basically reduce the rendering time into like 60 frames per second, so which is really enabling some kind of the real-time rendering with this kind of the neural net based some kind of reconstruction. And here the basic idea is that instead of like using some pure the implicit representation, we are basically having some sort of the combining some explicit representation, which was basically using some kind of ellipsoid, as I said in the previous slide. So in the underlying of the scene, we are having this kind of some so ellipsoid structure. If we just directly render those kind of the ellipsoid, then we see those kind of things. But when you basically combine some sort of some neural the properties attributes for each of the the Gaussians, and basically use some kind of the volume rendering the equation, we can get much kind of the realistic images as the output. Yeah, so basically what we want to do, what we want to achieve some kind of the neural rendering the pipeline. Basically, we want to get some kind of the very accurate the rendering the output. So basically, when we render some kind of these things from some kind of the viewpoint, we want to basically match the rendered image with the ground truth the image that we have. And also the fast rendering is also one of the important part in the neural rendering. So if we use the typical the vanilla the pipeline, you can see that actually it takes lots of the time because you need to shoot the ray for every single pixel and need to sample the points over the ray and basically integrate all the things over the rays. This is basically involving lots of the time for the computation. So the question is that how we can also achieve this kind of the fast rendering speed even in the real time. And also the memory efficiency. Obviously, the NERF is kind of good in terms of achieving the memory efficiency because everything is represented into the implicit function. Like if we start to basically incorporate some kind of explicit representation, then typically we have some kind of a trade-off. So as we basically have some faster the computation time, we should be the case that we are also taking the more the memory. So here also the question is that while having the fast the computation time, how we can also reduce the memory consumption. So that's also the one question, and also how much is to integrate into some kind of existing graphics. The pipeline is also one of the questions. And for that, basically, Gaussian splitting was kind of the algorithm that was basically achieving all these kind of things. So the Gaussian splitting basically provides some basically very high accuracy in terms of like matching the PSNR of kind of images with the other state or the neural methods. And also it's super fast. As you can see, it's basically rendering things for like rendering more than 60 frames of the images per second. So it's really fast, and also for the reconstruction, it's taking like much less time compared to the vanilla nerve. And also it's quite the minority efficient, which can be so many kind of the Gaussian split outputs can be actually rendered even in the mobile devices. And also, interestingly, the Gaussian split became very famous in terms of like being integrated into many graphics engines, into the Unity, Unreal engines. For those cases, you can see some kind of plugin of the Gaussian split now. So it's really becoming really popular in many kind of graphics pipelines. So what's the basic idea for the Gaussian split? So basically, the Gaussian split was inspired also by some kind of old work. So that's why I'm saying that there can be some also the hidden gems in the kind of the old work. So actually, Gaussian split is based on the point-based rendering, which was first introduced in the 2001. So there's the title here. So it should be like the 2001. And at that time, like more than 20 years ago, like people actually started to look into some kind of the ideas about the point-based graphics in some multiple reasons. So that actually one of the reasons that why people started looking into the points-based graphics is that at the time we start to see some kind of some advances in the the GPU the techniques in terms of now the GPU at the time can render like more than 100 millions of the purchases per second. Which was actually quite fast, the completion, the speed at the time. And if you also start to basically describe all the kind of details of the 3D shapes, then only the triangles becomes very small. So here that question is that like instead of like using the triangles in the mesh, would it be possible to basically utilize some different types of the primitives for the fast for the rendering? So especially in the case that when you can basically handle lots of the vertices, why don't you just directly use the points instead of like having the faces, especially when you want to basically describe all the details. So this was like basically one of the questions that people had at the time, like why don't you just use the points instead of the mesh faces? And also what we started to see at the time was that like people also started to have some really good 3D scanner. So these are some kind of these the outputs of like rendering some kind of the scan the object. So this was also the very famous project at the time, which is the digital the Michelangelo project, which is really basically 3D scanning some kind of the statue like the David statue here by the Michelangelo. It's kind of like idea like we are converting all these kind of some physical object into some kind of some digitized kind of things. So you could see that basically at that time, like people just made this kind of giant 3D scanner, which is really giving some very high accuracy. So it's really like capturing this like 5 meter the statue with the 0.25 millimeter the accuracy. So which is really accurate, right? And capturing this kind of entire the statue with the 4 million points. And then here the question in the graphics was basically how we're gonna basically handle this kind of the very high resolution the point cloud. So if we also start to convert this into the mesh, then it will take lots of the computation time. So the question is like, why don't you just directly render this kind of point cloud? So that was also like the case, like stimulating the idea of the point-based graphics. So I also recommend you to check out this kind of old work. Even there was kind of the conference with the point-based graphics and lots of the research at the time. You can also check out some kind of the course note describing this kind of some new techniques. So the basic idea in the point-based rendering is that we are basically having the points as kind of the samples over the surface. And each of the, these kind of the points will basically describe the geometry information and also encode some kind of the some reflectance the properties, like some kind of diffuse colors or something. But obviously those kind of points are not providing any information about the surface. So there's no kind of the connectivity information. And also there's basically no texture map or any bumpy maps or any kind of the surface information. So, and these kind of the points are basically called as kind of the surface element or subfield, or basically, surface split as well. So there are basically some multiple terms that call this kind of the point. So the basic subfield basically includes the information of the position and also the color information. And here the question might be is that if we only have some kind of a set of the points where basically each of the point only has the position or the color information, using this kind of the point cloud, basically how are we gonna basically do some kind of the rendering, right? So basically when you do some kind of the rendering, we would like to assume that there is some kind of the surface information, right? Then basically if we want to do some kind of rendering with the surface information, this kind of the surface basically need to be interpolated in some kind of regions. So which means that the surface also should have some kind of the surface area information. So also people started to basically extend the basic kind of the components of the subfield into the disk, basically having the position and the color, and also defining the normal and also the radius as well. So in terms like treating each of the points as kind of the disk. Then what we can see is that now we are treating all these kind of like points as like having a set of the disks and replacing the triangles with the disks in terms of having the disk as kind of the primitives for the rendering. And then we can basically use the typical kind of rasterization or the ray tracing the pipelines with these types of the primitives. So this is the basic idea. And these subfields were introduced in the 2001 or something, and then also revisited in the recent rendering the literature. So this was also one of the some sort of the earlier the work using the surface the splitting kind of the idea in terms of like doing some sort of the 3D reconstruction with the differentiable the rendering the pipeline. So you can also check out this work. But the basic thing is that in the success of the nerve, what we could say is that it's better to represent all the 3D thing not into the surface, but into the volume. So that's why we are also using the volume rendering, right? So here the basic idea is that instead of like when you have some sort of the volume split instead of the surface split, how we can also utilize this volume spread in some kind of the volume rendering the pipeline. So this is the basic idea in the Gaussian split. Why also there are tons of some kind of engineering in terms of like doing some real 3D construction. So whether we have some kind of the surface split or like the volume split, basically utilizing this kind of the split and having some hybrid representation is good in terms of there are some kind of these two major advantages. The first thing is that like when you have this kind of some explicit primitives, we can directly use the rasterizing the pipeline. So we don't need to shoot a ray and sample the points along the ray and basically evaluate some kind of input function to look up all these quantities. So what we are actually going to do in the Gaussian split pipeline is that we are going to really like render all these primitives into the 2D plane using some kind of the rasterization the pipeline, and then do typical kind of the process in the rasterization pipeline. So this is good in terms of that we can really reduce all this computation time, and also we can utilize the typical graphics pipeline with all the shader language, all the things. So this was kind of one of the advantages in terms of that we can really reduce the computation time. And also the other kind of the major advantage is that so for all this kind of the neural network the pipeline, we need to basically have the camera pose information, right? So here, basically, we all assume that given a set of the images, we have the camera pose information and do some kind of 3D reconstruction. And here the question might be is that how we obtain this kind of the camera pose information. So for that, we are using some kind of algorithm in the structure motion. So we are not gonna go into some details for the structure motion, but if you're also interested in this, you can also check out the lectures in the machine learning for 3D data, the course. But actually, the thing is that as the output of the structure motion, we are not only getting the camera pose information for the images, but actually the intermediate steps in the structure motion basically involves like finding some sort of the corresponding the pixels across the images and shooting the rays to find the intersection point in this 3D space. which means that actually as the output of the structure from motion, we are also having some kind of the some sort of 3D reconstruction, but which is basically becoming some sort of the sparse the point cloud. So this part, the point cloud itself is basically not useful to directly let it be rendered into some kind of real images. But still, this kind of sparse the point cloud can be useful as some sort of the initial the volume display, so that we can start to do some kind of optimization with this kind of initialization. So here the major advantages like having this kind of like using this like split the representation is that we can utilize this kind of some sparse point clouds coming from the structure from motion as kind of the initialization. So we are starting from some sort of the some rough 3D reconstruction and basically doing some kind of the refinement over the optimization. So this also basically allows us to basically achieve some 3D reconstruction more basically faster way. So these are basically would be some kind of major advantages having this kind of split representation. So yeah, then here the question might be is that we have some this kind of a set of some sort of the volume display. So how we are going to basically render all the things into this using some kind of volume rendering equation. So this is kind of the main part that we are going to discuss for today. And before we move on, do you have any questions on this? No questions. So actually, the main thing that we are going to discuss for today is basically how we are going to define this kind of the volume split, and also how we are going to use the volume rendering equation in terms of doing some kind of the rendering. And for that, we are basically going to follow some kind of the ideas in the old paper, published in the 2002. So you can also check out some more details for the formulation in this paper. But we are going to go step by step in this old work in terms of like how we do some kind of volume rendering with the volume displays. So let's first see like how we first define this kind of the volume split. We are going to basically assume that each of the volume split basically have the opacity information and the color information. So these are basically something that we are basically evaluating with the neural network, the implicit function, right? But now we are assuming that each of this kind of the volume here, the volume split, which looks like some kind of ellipsoid, is basically including the opacity information and the color information. So for basically the color information, you can define the color as kind of some constant value for each of the volume split. You can also make it as kind of the view dependent information. Then it's exactly following the nerve the equation, having some sort of the radiance information. So the difference with the nerve is that in the nerve, those kind of the quantities were basically returned from some kind of the neural network as kind of implicit representation. So now we are having the explicit the opacity and the color information, which are basically encoded for each of the split. And additionally, for each of the volume split, we are basically having this kind of the elliptical, some Gaussian the corner, which is defined with the center point, P, and also the covariance the matrix, the V. Obviously, it should be the symmetric the matrix. So we are basically, in the 3D space, having this kind of the position, the center point, and also kind of the 3D axis, define some kind of local coordinates, and also the scale information, which are basically defined with the covariance matrix. Makes sense? So given this kind of the center and the covariance matrix, we are going to define the elliptical the Gaussian corner like this. So which is really making some kind of the ellipsoid shape of the Gaussian corner. And basically the meaning of this kind of the Gaussian corner is basically is calculating some kind of the amount of the influence from the given the volume display to the any of the point in the 3D space. So it becomes some kind of the weight information for any point in the 3D space, how much of each of the volume split will affect that point in the 3D space. So becoming some kind of the distance based on sort of the weight information from the split to the any of the point in the 3D space. Makes sense. So we are going to have lots of these kind of the volume splits in this 3D space. And what we are going to do is that we are going to rasterize all this kind of Gaussian split from the object coordinate system into the rate coordinate system. So these are also the things that we have seen in the second lecture, like having some kind of rasterization in the pipeline. We are having some kind of the model view transformation and also the projected transformation. So the object coordinates is kind of also called the world coordinate. So every time when you change the camera pose, we are having some kind of some sort of the camera the coordinates this system. So we are also converting this into the rate coordinate system that we are also going to see in the next slide. Okay. So we are going to have these notations. X is for the objective coordinates, and F is basically the model view the transformation, converting the objective coordinates into the camera the coordinates. And G is the project transformation, also converting the camera coordinates into the ray coordinates. So please check out this kind of notation that we are having here. So here, basically, what do we mean by basically ray coordinates? So this is basically nothing but having some sort of the projective the transformation, projecting all these things in the 3D space into the 2D. But the only thing is that for this the project transformation, we are having basically this extra term. So as you can see, the first two terms is basically nothing but projecting the 3D things into the 2D the coordinates. Obviously, we can have some different sort of the projective transformation, but let's think about the simplest case. We are having this kind of like simple projection into the 2D space, but as kind of the extra the coordinates, we are basically having this like distance term. So this is kind of like some small difference with the typical the rasterization the pipeline that we are seeing in the OpenGL framework, right? So yeah, so this is our definition in this simplistic case that we are having this project transformation, projecting 3D things into 2D, and having one more basically the coordinates, which is about the distance. Great. So here also one key thing is that so we are defining the center point and the covariance matrix for every single the Gaussian split for the volume spread, right? Then here the question is like, in which space we define those kind of things? Obviously, like those quantities will be defined in the object coordinate system, right? So we are having some kind of the world coordinate system, and every time when we basically choose the camera pose, we are going to determine the camera coordinate system and also the rate coordinate system. So which means that for every Gaussian split, we are going to first define the center point and the covariance matrix in the object coordinate system, right? So which means that if we want to compute this corner for any kind of the point, if this point was basically represented with the objective coordinate system, then we can just compute this, right? But if the point was basically having the rate coordinates, then we will need to first convert this into the camera coordinates and the object coordinates and calculating this. Is this clear? Just nothing but just changing the coordinate system. So just keep this in mind that we are having this notation. So x basically indicates object coordinates, x prime indicates camera coordinates, and x double prime indicates like rate coordinates. So depending on where we are basically defining point in which coordinate system, if you have the point defined having some kind of rate coordinates like this, then you will need to convert this back into the object coordinate first, and then calculating this kind of the Gaussian corner. Great. Any questions on this? So please keep this in mind. So we are moving on to slightly more complicated kind of things. But so let's see. Given any kind of the 2D pixel xy with the xy coordinate in the rate coordinate system, now we'd like to compute the volume rendering equation. So this is exactly the same equation that we have seen in the NERF, right? We're having the color information, opacity, and the transparency. And the transparency was defined with opacity like this. So instead of like having the time, we are going to now have the distance from g here. And this distance, by definition of the rate coordinate system, this distance becomes the z coordinates in the rate coordinates, right? So given any kind of the 2D pixel defined with the xy coordinate, we are shooting the ray along the z-axis, basically having the z coordinate here. And if you combine this x, y, z, that becomes our the ray coordinates, right? This is nothing but just having the same, the volume rendering equation. Now here the question might be still like how we calculate this color and the opacity information with the given the set of the volume displays. So given the set of the volume splits, what we are going to do is that we are going to define the opacity as the weighted sum as follows. So the only thing is that since now we are having the points which is defined in the rate coordinate system, we are calculate the weight which is defined with the Gaussian kernel like this, right? So we are first sending this kind of the point defined in the rate coordinate system into the ordinate coordinate system, then we can calculate the weight, which is the influence from each of the split into any kind of point in the 3D space. Then basically the opacity is calculated as kind of the weighted sum for each of the volume split. Is this clear? So you can see that I just like introduced some kind of the new term, G top line, which is nothing but just like rewriting this part like this. It's just like making some sort of the simpler form, right? And also basically the multiplication of the color and the opacity will be also defined as kind of the some weighted sum as follows. With some kind of approximation that all the Gaussian split has some kind of the constant color along that direction. So these are basically some sort of the definitions of the opacity and the multiplication of the opacity and color here. Right? So just keep this in mind that we're having some new notation which is basically calculating the weight for the point in the rate coordinate system with some kind of the Gaussian kernel defined for each of the split. For the ice display, we can compute the weight like this by just feeding the points defined in the rate coordinate system. Then here the question is that can we then rewrite the volume rendering equation by replacing this part like this and also this part like this? So let's do some kind of the exercise. Did you even get the results like this? So we are basically kind of like tweaking the color and the opacity term to be constant for each of the split, while basically during this the quantities with the weight, which is defined with Gaussian corner here, right? So in terms of that, we can basically rewrite these things in like this. And also this is the case that we are yeah also replacing these two. And also instead of like taking the exponential of the like minus sum of these things, we can change this as like taking the product of the exponential of the some kind of quantities here, right? So we just like rewrote the volumetric equation like this. And we would like to further like simplify this equation with some kind of assumption and also some kind of the tricks. So there are basically some kind of the assumption and the approximation and many kind of things, which means that it doesn't need to be simplified in this specific way. But let's basically see the exact formulation that was introduced in this specific paper. Well, first of all, basically, we are going to introduce some kind of the new term, which is basically indicating the integral of the Gaussian split along the ray direction. So if we basically take the integral of the Gaussian split along that the specific ray direction to the end of the ray, then we're gonna basically get this quantity, like defined like this. Just to simplify the formulation, we are also going to use the first order, the Taylor expansion, to simplify the exponential minus x is kind of like approximating this as kind of 1 minus x. So this is also kind of the approximation. And also basically one big assumption that we are having is basically the assumption of the local supports and the zero overlap across the volume the splits. So what we are going to assume is that we are first assuming that all the volume splits are basically sorted in the basic order, that the first one is the closest one and the last one is the farthest one. Okay. So any kind of a point in the 3D space, what we are going to assume is that if the weight from the ice, the volume, the split is non-zero, is basically greater than the zero, then we are going to assume that the weight from the next the splits after the ice the split becomes zero, right? So which means that if we are having any kind of the point which is basically affected by like one of these split, then we're going to assume that all the other the splits which is like coming the next are basically not affecting to this point. So this is basically some kind of very strong assumption that we are going to utilize to simplify this equation. So in this equation, what this means is that if this value is basically not zero, basically we are having some kind of the influence from the ice flat to this point, then what we are going to see is that basically this quantity becomes zero because there's no effect for here, right? So this means that this whole term becomes zero, and we are just taking the exponential zero, and which means the one, right? So this is the very strong assumption that we're going to utilize. So given this kind of the three kind of the definition and the approximation and the assumption, we are going to also see the simplified the version of the equation. So let's rewrite this equation again by having these kind of things. So we are replacing this like this and also having the approximations and the assumption here. Based on that, if we rewrite the equation, what would be kind of the some simplest form that we are going to get. Also here, one quick thing is that if we are like calculating this equation for the point x dot prime here, which is for the ice split, and if we calculate this term in the exponential for some any kind of the previously split, it becomes the same whether we take the integral of this term over the entire degree or until this point, because we also assume that the previous split is not affecting to the points, which is like affected by the next split, right? So maybe we can go one by one. So from the local support assumption, what we can do is that we can replace this to be I, right? Because like for the split after the ice one, the basically this term here, yeah, not sure whether you can see my mouse point. This term in the green box will become 0, which means that exponential of this 0 becomes 1. So we can basically ignore this kind of term, right? We can first replace this to be I, and then we can also replace this to be Z max. Because for the old split, before the ith split, like it's the same whether taking the integrals to that point or taking the integral over the entire array, right? From the local the support assumption. So also one thing is that you might be confused. We are having the x double prime term here. We're taking the while taking the integral of the z. So actually here the x double prime is the ray coordinates, which is having the x, y, z coordinates. So we are taking now integral over the z axis, right? So then now we can say that like we are replacing this to be I, and we have the z max. Then we can simply like rewrite this part with the qi term that we introduced. And we can also do the same thing here as well. And then we are also replacing the exponential minus x, approximating this into the 1 minus x, right? Then what we get at the end is basically we are having this kind of term. So we replace the, and to be I minus 1, actually, sorry. And then we are also replacing this to G max so that we are having the Q J term and also the Q I term. And then approximating the exponential of the minus x as kind of the 1 minus x like this. So this is the very basic equation that we are using for based on the split-based rendering. Obviously, you can see that there are lots of kind of assumptions that is basically involved here. So which might mean that we can also introduce some kind of the new equation. But until this point, do you have any question like how we came up with this equation? So what we can see is that we are having the color term here and the opacity term here, which are basically some attributes defined for each of the Gaussian display. And we are also having the function defined for each of the split, which is taking the ray coordinates and returning some kind of the weight, the term here. Any questions on this? Yeah, I guess if you okay, you're like following all this equation, then here the remaining the question is that how we exactly calculate this Q term, right? Which was the case that we are taking the integral along some kind of a line passing through the ellipsoid like this, some elliptical corner. So when you basically have this kind of some elliptical the corner, the Gaussian corner defined with the center and the covariance matrix, how we are also going to compare this? Well, I mean, yeah. So this integral to basically what we are going to do is that to like make it easy to calculate this integral. Now we are going to approximate this term as kind of some sort of the transformed the Gaussian the corner in the ray coordinate system. So these are the cases that we are having defining the Gaussian corner in the object the coordinate system with the center point and the covariance. But by basically transforming this kind of the ellipsoid into the ray coordinate system, we transform the center point and the covariance matrix. What we are going to do is that we are going to approximate this kind of the kernel of the output with basically the kernel of the computation in the ray coordinate system with some kind of the scaling vector. So this is what we are going to do. So let's do this like step by step. So let's first see like how we can do this from the conversion to the object coordinate to the kernel coordinate first. So like when we have this kind of the the point defined in the object space, now we are going to like calculate the same thing with this kind of like the weight computation in the kernel coordinate system with some kind of scaling factor. So let's do this first. So what how we define the model view transformation? So typically the multiple transformation will be basically defined as kind of the affine transformation, which is that having the linear part, linear transformation here, and also the translation, right? So when you define the mobility transformation kind of function, denoted as the f here, the f will become the ws plus t, and then the inverse conversion. Wait, it should be right here, right? The convert from the camera coordinate to the object coordinates will be defined like this. Then based on this, without any kind of derivation, let me first show that, so now we are going to transform the center and the covariance like this. So let's say like this is kind of the transform center point in the camera coordinate system, and the V prime is also the covariance of the matrix defined in the camera coordinate system. These are like all defined like this. And what we are going to do is that by like computing this Gaussian corner in the camera coordinate system, we are going to see what's the scaling factor in a way that the weight that we are computing in the camera coordinate system matches the weight that we are calculating in the object coordinate system. So given this definition of the P prime and the V prime, basically some transformed position and the covariance matrix is in the camera space, what should be the scaling factor, the C prime here? So let's quickly calculate this. So these are some kind of the hint. So also the way that on how we calculate this is that we know how we can define this, right? And we can we know like how we can calculate this as kind of the uh, inverse of the model transformation, which was defined as kind of like inverse times minus t. So we can just like simply plug in this into this equation and see what we get. So, okay, as we are running out of time, so let me first move on, but you can also check out some more details for the formulation. So this is basically nothing but we are just plugging, this inverse of the model of the transformation into the x and also the p here. And what we can see after like all the derivation is that it becomes like calculating this weight becomes the same. That we are calculating the weight with the transformed, the center point and the covariance matrix defined in the camera the coordinates, then we will need to basically multiply this kind of the scaling term, which is basically coming from some kind of the scaling part of the linear transformation. So which means that there was no scaling, only rotation in the multiple transformation. There is nothing that we need to basically multiply here as kind of scaling term. But basically here, the basic idea is that if the transformation was basically a affine transformation, we can basically simply like redefine, defining the same the Gaussian, the corner in the new space with some transformed the center and the covariance the matrices and covariance the matrix, and then basically multiplying this kind of the scaling the vector. So this is kind of the doable. But here the problem is that like for the next step, for the conversion from the camera coordinates to the ray coordinates, how can you do the same thing? So here the problem is that actually this transformation is not a affine transformation, but actually the project transformation. So actually there's no way that we can define the same, some kind of the Gaussian, the corner that will basically give some kind of the same, some sort of the continuity outputs with the camera coordinates. So what actually we have done in the previous case is that we are defining some kind of the same the Gaussian corner in the camera coordinate with some kind of a transformation. But in this case, like when you have some kind of project transformation, it's impossible to define the same the Gaussian corner as kind of Gaussian corner in the linear space. So what we are going to do is that we are going to approximate the project transformation as kind of be a affine transformation for each of display. So this is kind of like done for every single display. And let's think about like this specific, the simplistic case of like having this specific the project transformation. Then what we are going to do is that we are going to approximate this project transformation using the first order detail expansion. Then we get this kind of some sort of the approximation for the same the project transformation, right? So what we can say is that this becomes like having some sort of the translation part and also the linear transformation. And this linear transformation is basically defined as kind of the Jacobian matrix. So if we basically calculate the Jacobian matrix of that specific transformation, then we are having this specific Jacobian matrix. And if we basically compute the first order detail expansion for the center point of the display in the camera coordinates, then we can say that given the project transformation can be approximated into this point, still having some kind of the linear transformation and some kind of the translation, right? So in this case, that when we have some kind of linear transformation and the translation, we have seen like how we can also calculate some transformation of the center point and the covariance matrix and also the scaling factor, right? So for this specific case, like having this linear the transformation, the translation, can you basically also answer like what should be basically some the transformed center point and the covariance and the scaling factor here? So previously, this linear transformation was W, and the translation was simply T, right? So when you have the linear transformation W and the T here, then P prime was basically W P plus T, and the V prime was W, V, W, transpose. So if we do the same thing, like if we now define the P dot line, then this becomes like, we just plug in P line into this equation. If you just plug in P line into this equation, then these two will be canceled out. Then the P dot line will become G P prime. And also when you have some kind of the V prime, the V double prime will also become JI, right? V prime and JI transpose. Just following the exactly same thing that we have done in the previous transformation, right? So that means that we are going to have this kind of the transformed the vertices, the center point, and transform the covariance matrix and the scaling term from the converted from the camera coordinates to the ray coordinates. So if we combine these two, like from the object coordinates to the ray coordinates, then what we are going to see is that now the P dot line can be defined like this. From the center point defined in the object coordinates to the kind of the points in the ray coordinate system. And also the covariance will be also converted like this, multiplying like the matrices like this. And then the scaling factor also will be defined like this. So here the thing is that W was the linear transformation part coming from the model of the transformation from the camera pose. JI is basically the Jacobian matrix that we are calculating for each the Gaussian split. So by multiplying those kind of the quantities, now what we can do is that if we come back to this equation in terms of like how we are going to calculate this with some kind of the Gaussian split defined in the ray coordinate system, then we can basically replace approximating this part into this formulation with transformed the center point and the transformed covariance matrix defining the ray coordinate system. Then we are basically having this with the transformed center point and the transformed variance here. Then once we basically have all this kind of like transformation, the good thing is that this integral becomes nothing but just like taking the integral along the z-axis. So we can just ignore the x and the y-axis, just taking the integral along the z-axis, then that becomes our kind of the answer for calculating this stuff. Any questions on this? So yeah, so it basically, as you can see, involves some kind of the slightly complicated some equations. So I also recommend you to check out this. So when you typically talk about the Gaussian split, like people don't speak about like this kind of some underlying some calculation. It's more of some kind of engineering. But actually, if you start to look into some more details of like all this equation, then you can see that actually this involves lots of kind of some approximation or some kind of assumption. So this might mean that we can also enter some kind of the better equation, like calculating all these kind of the volume measuring equations using these splits. And here also like one quick question is that when do we need to update the center point and the covariance matrix, the transformation like those things? We can see that actually this equation involves the W part and also the JI. So these are basically also coming from the camera pose. So which means that if you have some kind of the rotation of the camera pose, then you will need to basically update all these kind of quantities, but not for the every single the pixel, for the given the set of the Gaussian split. So the rendering the pipeline, what we need to do is that once you have any kind of the camera pose, then every single the pixel, you will first need to collect all the set of the subset of the splits that is basically falling into that specific pixel. Then we will need to sort all these kind of splits based on the depths, the order, right? And then we are calculating this information with given the specific the camera depths, and then we are calculating the volume rendering equation. So this is the kind of some procedure that we are doing some kind of the rendering the pipeline. And if we also see how we exactly train all this like the Gaussian split, I also recommend you to check some details in the paper. But we're gonna basically initialize this split based on this part of the point cloud coming from the structure from motion with some kind of the isotropic the covariance matrix, and then basically updating all these kind of split parameters using some kind of the loss and the backward propagation. And there are also some kind of steps that we are also cloning these splits for some kind of the under reconstructed regions, and also splitting these splits in the over reconstructed regions. And so there are actually lots of the engineering in terms of like how we can get some kind of the define the outputs of this 3D construction. So today we dig into some details about how exactly we calculate this volume density equation with these splits. And in our the gas lecture, I guess we're gonna see some more kind of the higher level the ideas in terms of like how we can make some kind of better the reconstruction and the rendering the systems. We're gonna also discuss some more the papers in the paper presentation based on the Gaussian split. So until this part, until the Gaussian split, this will be the scope of the midterm, and also we are going to have the midterm next week. So if you have any questions about the midterm, any the materials, then we discuss so far, please post the questions in Slack, then we can also go over with the questions. Any questions? Okay, so yeah, so this is the end of the today's lecture. And as I said, there is no lecture this Wednesday. We're gonna have midterm next week and break for the week after the midterm. And we're gonna resume the lecture on April 29th. So I will see you the last week of the April. Thank you. Bye.